So as we move along from the last time's discussion, today I got two parts in my presentation. The first one is that this is a very fascinating evolution for the last about 100 years, as I mentioned last time. But exactly what are the computer science tipping points? What exactly happened in the field of mathematics and computer science and engineering that really has brought us today? And the lessons are important. Personalities are also important, but not as important as the lessons or the contributions of these people, because it is the contributions which really give us and guide us in terms of doing the further development in this field. So first I will recap the contributions, and the second part I want to show is that when you want to interact with the machine, what kind of mathematical background is required. So far you have studied algebra, you have studied trigonometry, you have studied arithmetic, and you will find that it has been learned in a certain way because it was presumed that you will be the person who will be dealing with it. Suppose the mathematical processing has to be done by a machine, obviously the kind of mathematics that you have to do is slightly different than the mathematics that you have learned and the way you have approached that mathematical problem. And I will give you several examples. These are called as strategies of problem solving. And this is a sort of a review. Obviously each one of them takes an enormous amount of time to become expert or study it in detail, but it gives you a bird's eye view of what kind of shift that you require in your mindset when you are studying these problems. When I give you a certain mathematical problem, you will be solving several problems in the homework as well as in the lab assignments. Your attitude, your approach has to be different than what kind of mathematics you have studied either through present one or two courses or in the schools. So this is what today's lectures will be about. So I'm going to throw you some pictures so that you associate what you have to remember about it. As I told you earlier, that the pioneers of computer science were mostly the Europeans, and the endeavor at that time was to create a mechanical contraption, a mechanical device which is used as a machine. It was earlier called as a difference machine or analytical machine, etc., etc. And this happened mostly in Europe as well as in Britain. And the person who is credited as the pioneer in computer science is a countess, and her name is Lady Ada Lovelace, A-D-A-L-O-V-L-A-C-E. Okay. Now she was a countess. She was the daughter of a poet. I don't know how many of you know Lord Byron. You know, he was a very famous British poet. She was his daughter, and she had both the artistic bent of mind as well as the mathematical bent of mind. And in these weekend meetings with the rich people, she used to go and understand things, but she was not allowed to publish her work. Whatever work she did, she was not allowed to publish it because she was a lady. And subsequently she wrote the notes actually, and these 4 notes that she had written, actually she reviewed a paper, and while reviewing the paper she had her own thoughts, and she said, can I publish my paper? And the editor told her that yes, we can take your thoughts, but put it in the form of notes. And these notes 1, 2, 3, 4, if you look at these 4 notes, they are really the most important contributions even today in computer science. So her contribution has been phenomenal, and her life is also very interesting. The first principle that she enunciated, note number 1, was a general purpose programmable machine can be built, and the word computer came along. So up until now people were building machines, but it was only for one purpose, one machine, another purpose, another machine. And she says that is not required. As a matter of fact, you should have the built-in flexibility in a machine. In other words, the machine should be so general purpose that I can program, reprogram, or subsequently modify as much as possible. So the fact that you can build a programmable machine for solving the problems, and at that time she had 1 or 2 mathematical problems. As I last time told you, the one which was used very frequently was the Bernoulli's numbers actually, and the Bernoulli's numbers was one of the reasons, and then 3, 4 other mathematical problems. But people were building different machines, and she says, no, that's not required. You should have only one machine to solve all the problems, but program it depending on the problem that you want to solve. Now, this is a very important principle at that time, and obviously this has been followed when the subsequent development of computing over the next 100 years happened. We are talking about 1839. I mean, remember that this is the first half of the 19th century. Now, then the next thing she said is that, and this is a very important principle that she enunciated, that don't consider this only a game of numbers. It's not arithmetic only. Any information which can be represented logically by symbols can be processed using programmable machines. So basically now, as you see, that we can process digital signals of all kinds. We can process digital signal of music, we can process digital signals of graphics, we can process digital signals of speech, we can process digital signals of alphabets, we can process digital signals of numerals. All these aspects originally was thought by Ada. The Ada Lovelace said that if you can discretize, if you can digitize the information, and the second most important part is that how do you represent this information? This representation of information, now today there is a big field of data structures, and in your course you will find that you will study different kinds of data structures which are used for representing. So if I got a graphics picture, how do I represent it in the computer? If I got a musical signal, how do I represent it in the mind you, the computer only stores zeros and ones. It has got the circuitry, it has got the chips, it has got the RAM or many other things, but it can only store zeros and ones. Now if you look at the picture which has got color, which has got different pixels, and therefore in order to digitize that information, so obviously this representation of a picture is the logical symbol representation. So we manipulate the symbols as well as we manipulate the zeros and ones. Zeros and ones is a digital symbol in some sense. So you will find that even though she had no clue about the music and the graphics, and all these developments have happened in the last 30-40 years. There was no graphics before 1950. There was no music along with the computers before 1960. To some extent. So you will find that even though she didn't have the inclination of these other signals, she was able to enunciate a very basic principle that if you can represent that information in the logical form, in the form of symbols, then you can manipulate, you can process that information which is a symbolic information. And God knows what will be the next one. So you will find that these are the very fundamental principles which can be used even for future developments in the years to come. The third most important part is that of an algorithm. Now, a procedure, a very ironclad procedure, when I have to program a machine, when I have to give the instructions must be unambiguous. It must be very clear. There cannot be ambiguity in a computer program. Let me tell you, one thing you must remember is that there is never ever any ambiguity in a computer program. The computer program remains very unambiguous, and then you realize, oh, this is the way it could have been thought of, because you have not thought so. But the machine looks at it in a very precise, in a very unambiguous manner, a sequence of such instructions, and I'm sure we will be going through later on in a very formal definition of the word algorithm, and the algorithm will have some input, output, then the steps that we have. There cannot be ambiguity in the steps that you write. Such a thing can be written down and then coded in the form of that program. This was enunciated as the third principle by Lady Ada Lovelace. Okay? And the fourth principle, which even today remains a very valid question, which has not been answered so far very successfully, is that she also raised the issue of whether machines can think. Can machines think? And even today you will find that the thinking ability of the machines is still a question. What is meant by thinking process? How does the thinking happen? There are different ways, and we will look at it, some of the things. Even then, where there is a certain amount of creative thinking. So if you look at the entire gamut of activities of thinking, and a sort of a small child of such an endeavor is done through artificial intelligence. You have got a lot of work done through artificial intelligence. Unfortunately, not in this course, but subsequently you will be able to learn such things. But those techniques have made an attempt to see how machines can think. And if you ask me today, you have still a problem which is not yet resolved very successfully, is to decide whether the machines can think. At that time, Ada Lovelace declared, no, machines cannot think. And the second thing that, of course, people are trying to work out is how to develop machines that can think. A small attempt, so far as the work done in artificial intelligence is in front of us, people can look at it, but still not answered this question.